Hello everyone, thanks for stopping in. Today we're going to be talking about the introduction to probability. And so for this section, what we're going to want to do is we're going to want to have a bunch of different definitions first. And the first definition is an event. An event is a collection of outcomes for a procedure. And in probability, a lot of times we like to think about things that are left to chance, like rolling a die, right? When you roll a die, it comes up a 4. That's an outcome, right? And it's determined by chance. And that is what we want to look at with probability. So the event I was concerned with there was rolling a 4. Now my event could be rolling an even number, right? Then I could have 2, 4, or 6 on my die, right? I can have different events. So an event is a collection of outcomes for a procedure. I can have any collection of outcomes. A simple event is an outcome that cannot be broken down into simpler components. And so an example, rolling a 4 is a simple event. I can't break that down any farther. But I also said, what about rolling an even, right? 2, 4, or 6 would count for rolling an even number. Now, these simple events are 2, 4, and 6. The event is rolling an even number. That's the difference between a simple event and an event. It can't be broken down into simpler components. And a sample space is the collection of all simple events for a procedure. The sample space is all possible simple events for that procedure. That is what a sample space is. So if you're doing something, rolling a die, my sample space should be 1, 2, 3, 4, 5, and 6. Because that's the collection of all possible simple events, right? Now let's take a look at an example. We're going to construct a table pertaining to a single birth versus 3 births. So what we're going to do is we're going to have procedure we're going to have the events within that procedure, and then we're going to have the simple events within that procedure. And there's going to be 2 of them. The first procedure is a couple having a single birth. And the other procedure is a couple having 3 births. So a single birth or 3 births. Now, there's different ways you can have a single birth occur, right? The couple could have a boy or a girl, right? Oops. Or a girl, right? Could have a boy or a girl. The simple events, well, simple events we usually write as a collection, so we put a curly brace. The first simple event would be having a boy. The second simple event would be having a girl, right? I can't break those outcomes down any further than that. However, with 3 births, I have some different possibilities. If I have 3 children, I could have 3 boys, or I could have 2 boys and 1 girl, or I could have 1 boy and 2 girls, or I could have 0 boys and 3 girls, right? And in the first example, I suppose we should go back and add 0 girls as well then, right? That's the number of ways that's the different events I can have for having 3 children, having 3 births. I could have 3 boys and no girls, 2 boys and 1 girl, 1 boy and 2 girls, or 0 boys and 3 girls. However, these simple events get a little trickier. So let's take a look at the simple events. The first one, we're going to write all simple events for having 3 boys. That can only occur one way. And that's having a boy, and then a boy, right? If I want to have 3 boys, I got to have boy, boy, boy. However, if I want 2 boys and 1 girl, I could have boy, boy, girl. Or I could have boy, girl, boy. Both of those result in 2 boys and 1 girl, don't they? Or I could have girl, boy, boy. All 3 of these simple events correspond to the event having 2 sons and 1 daughter, right? I can go son, son, daughter, boy, boy, girl, or boy, girl, boy, or girl, boy, boy, right? There's different ways the simple events can be broken down. Same with the next one, 1 boy and 2 girls. Well, I could have boy, girl, girl, or I could have girl, boy, girl, or I could have girl, girl, boy. All of those are the possible ways to have 1 son and 2 daughters, right? Then my last event, 3 girls, that can only happen one way, and that's if I have girl, 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 right? In that order. So the simple events, there are 8 simple events, 4 events, and 1 procedure for 3 births. For the other example, it's a single procedure still. There were 2 events which directly corresponded to the 2 simple events as well. So sometimes there might be overlap between events and simple events, right? So that's an introduction to the difference between events and simple events. Now, let's get some notation. It's always good to know what letters we use. Generally, we use the letter P for probability. And then we might use A, B, C, different letters for specific events. So I might have an event, and I might call it the letter A. Maybe the letter A corresponds to 3 boys and 0 girls, right? Then P of A, P parentheses A, is the probability of event A occurring. We use P of A to write the probability. Now, we might we might have a example here. Let's say we have the probability of rolling a 4. The probability of rolling a 4 on your die. You might also write that as just P of 4 when the context is clear, right? The probability of rolling a 4, we might just write P of 4 when the context is clear. This is how we will write probabilities. We'll have a P for probability, and then in parentheses you write the event you're looking for. Like I said, sometimes you might use A, B, or C as abbreviations for those events. One last note, 0 is always less than or equal to the probability of A, which is always less than or equal to 1. Probabilities are always between 0 and 1. They will always be between 0 and 1. That also means that 0% is less than or equal to the probability of A is less than or equal to 100%. You can't have lower than 0 or more than 100% for a probability. You can't have lower than 0 or more than 1 for a probability. The top one would be for decimals, right, when you're using decimal notation. The bottom one is when you're using percentage notation. So make sure you're clear on that. You can never have a value more than 1. Now, let's look at some different approaches to calculating probability. There are three approaches we will use in this section. The first is the relative frequency approximation for the probability. So, for this, you perform a procedure some number of times and note how many times did event A occur. So you do something a bunch of times and you figure out how many times did you get the result you wanted. And this has a formula with it. The probability of A is going to be equal to the number of times A occurred divided by the number of times the procedure was repeated. Number of times procedure was done. So for example, maybe I want to know what the odds of rolling into 2 are. So I pick up my die and I sit here and I roll it. You know, I got a 2. I got 1 2. And I keep rolling and I count how many 2s I get. And maybe I roll it 100 times. Well, I did it 100 times. Let's say I rolled, 25 2s. I can set up that fraction, right? This is the frequency approximation. Notice it says approximation. It's not exact. So this is an approximation. The second is the classical approach. The classical approach. So, in this example, if a procedure has, let's say, n simple events, each with an equal likelihood of occurring, then the probability of A. So a procedure has n simple events, each with an equal likelihood of occurring, then the probability of A is equal to the number of ways A can occur. If you have all of the simple events listed out, you can count how many of them are A, divided by n. The total number of simple events. For example, with the die, there's 6 possibilities on a die, right? And every side is equally likely. That's what makes it a die, right? It's, each side's equally likely. There's 6 total sides, so if I want to roll a 2, there's one way to roll a 2, right? I roll the number 2. And there's 6 totals. There's a 1 in 6 chance I will roll a 2. If I want to roll an odd number, there's 3 odd numbers, 1, 3, and 5. So it would be 3 ways out of 6 possible total outcomes, right? This is the classical approach. This will give you an exact answer, but it's important that you remember everything has to be equally likely. They need to have an equal likelihood of occurring. So always confirm that. Always make sure you know your possibilities were equally likely. If, for example, you have a event that is more likely to occur, you can't count that in classical approach. They all have to be equally likely. And the last is subjective probability, and here the probability is estimated using the relevant knowledge of the situation. And subjective probability is only used when we know something is really likely or really unlikely. A great example of that would be when I roll this die. Is it possible that it might perfectly balance on its edge and not roll on one of the numbers? It could, right? That could happen. Same with if I was flipping a coin. It's possible, pretend this is a coin, the coin lands perfectly on its edge, right? That's not super likely though, but it is in theory possible. The subjective probability might be 1 in a million, right? I'm using my relevant knowledge. It's super unlikely. Do I know exactly how unlikely? No. I'm just estimating, right? I'm giving it a good guess. Subjective probability is just an estimate. We use this when we want to know is something likely or not likely. Now, let's talk about rounding rules. Rounding rules for probability are going to be fairly consistent. We can have 3 possibilities. We can have decimals, percents, or fractions. These are the 3 different ways we can write probabilities. For decimals, you round to 3 places. 3 decimal places when you're working with decimals. You round to 3 decimal places when working with decimals. For percents, you round to 1 decimal place. And for fractions, you can reduce fractions. So we reduce fractions. And if you want, you can turn them into decimals or percents. That's perfectly fine. But for fractions, make sure you reduce them. So let's look at an example of a decimal to 3 decimal places. Maybe we say we have 0.258 as my probability. That's a decimal to 3 decimal places. Now percentages. This number as a percent would be 25.8%. That's rounded to 1 decimal place, right? These numbers are actually the same number, right? Decimals and percents are related. Now, that also means that I can write fractions. Maybe I have a fraction of 6 out of 8. There's 6 possibilities out of 8 total outcomes. Well, I would reduce that to 3/4, which I can also reduce to a decimal of 0.25 or, 0.75, or 75%. This is a 7. I'm just going to rewrite it, 0.75, right? With fractions, we can reduce them, and we could leave it as a fraction if we wanted to. If the question's asking us to write it as a fraction, leave it as a fraction, right? Or a decimal or a percent. You'll want to be comfortable going back and forth between all 3. Like, how do you transition between any 2 of them? Make sure you're comfortable going between decimals, percents, and fractions. Which we've already taken a look at in the beginning of the course, right? But they're coming back again. We want to be comfortable converting between them. Now, the law of large numbers is an interesting concept. It says, as a procedure is repeated a sufficiently large number of times, then and here we're actually going to relate 2 of our ideas. We're going to relate the relative frequency approximation to the classical approach. Then the relative frequency approximation will approach the actual value, which can be found by the classical approach, right? Will approach the actual value. And that should make sense. Think about it. If I want to know the odds of rolling a 6, and I'm going to do an experiment right now. I rolled a 1. My odds of rolling a 6 are 0% based on my experiment. That's not correct though, right? I know it's supposed to be 1 out of 6, but I just got 0%. I'm going to do my experiment again. That time I rolled a 6. So now the odds are 50%, right? I've done it twice and I got a 50% chance of getting a 6. That's the approximation, right? I'm doing an experiment. However, if I roll this die 10,000 times and count the number of sixes, I'm going to expect my answer to get closer and closer to the real value. That's why scientists repeat experiments, right? That's why you should always repeat your studies, because you eliminate the random chance factor. You find the actual values. So we can repeat things. However, we should know two cautions. The first is the law of large numbers. The law of large numbers does not apply to an individual application of the procedure, an individual outcome. And let's think about that. And this is what is commonly known as like a gambler's fallacy. Let's say I'm going to win big if I roll a 6. And I roll. I haven't gotten a 6 yet. And I'm like, oh, I'm due for a 6 now. Is that true? Am I due for a 6? No, the odds of rolling a 6 are still the same, right? Every time I roll the die, I have a 1 in 6 chance. It doesn't matter that I've already rolled a bunch of non-6s. When I pick it up to roll it again, it's equally likely, right? I could sit here and roll this die forever and never get a 6. That is possible, right? It doesn't apply to an individual outcome. That is a common mistake gamblers make, that I'm due for a win, right? I've been on a losing streak, I'm due for a win. That's not how probability works. Probability is a more complex idea than you're due for a win, right? Each roll of the die is a random outcome. I could sit here and roll 6s all day long also. I could roll 10 6s in a row. That doesn't mean I'm due for a loss. It's just unlikely that that would happen, right? But all outcomes can happen, right? We can have any outcomes. I could roll this 100 times and never get a 6. Is that likely? Probably not. But it could happen, right? It's random. Now, the second caution. Do not assume outcomes are equally likely unless you know. If we don't know, do not assume outcomes are equally likely when we are not sure of the probabilities. A good example of that would be if I wanted to roll 2 die. So I've got 2 die here. Is rolling a 7 just as likely as rolling a 12? No, because there's only one way to roll a 12, but I can roll a 7, I can roll a 6 and a 1, a 2 and a 5, a 4 and a 3, right? There's more than one way to roll a 7. Rolling a 7 and rolling a 12 on 2 dice are not equally likely. So I should not assume the probabilities are equally likely. I should justify they are going to be equally likely. Here they were not. On a single die they are though, right? Any outcome is equally likely to each other outcome. So be careful with those two cautions. So let's take a look here. In a recent study among 3 million skydiving attempts, it was found that 21 of those attempts resulted in a loss of life. Based on this study, what is the probability of perishing in a skydiving accident? So the probability of perishing, what is that probability? Well, I've been given a procedure. The experiment has been done 3 million times. I have done my procedure 3 million times. In that procedure, 21 of the attempts had the result in question. 21 of those attempts had the result in question, right? Where someone lost their life to skydiving. So, I can convert this number into a decimal. 21 divided by 3 million gives me 0. And it looks like there's 1, 2, 3, 4, 5 zeros, 0.00007. Or, if you want to make it a percent, you can multiply that decimal by 100, right? Or we could say 0.0007%. So, based on this study, is perishing in a skydiving accident likely? No, right? That's what they make parachutes, right? There's safety precautions in place. Does that mean that myself, who's terrified of heights, is going to be hopping in a plane and jumping out of it to skydive? No. But the odds are in your favor if you're going skydiving. It's very unlikely for a skydiving accident to occur based on this study, right? Based on this study we have here, it's unlikely for a skydiving accident to occur, right? That's what we just concluded. Let's take a look at another one. So that was the relative frequency approach, right? That was the relative frequency approach. Now, let's look on the next page. We've got a mother has given birth to 3 children. A mother has given birth to 3 children. I'm going to grab that first page. I've already talked about giving birth to 3 children, right? This information might come in handy. So let's see. What is the sample space for this procedure? So I need the list of all possible simple events. The sample space will be BBB, 3 boys, right? We've already calculated the sample space, all the possible simple events. If I hadn't already done this work, I would need to do this work right here, right? I would need to write out all the possibilities. So I'm going to copy those down. We can have 3 boys. Next we'll do 2 boys and 1 girl. Boy, boy, girl. Boy, girl, boy. And girl, boy, boy. Next we'll do 2 girls and 1 boy, which is girl, girl, boy. Girl, boy, girl. And boy, girl, girl. And then last we do the 3 girls, 3 daughters. Those are my 8 possible outcomes, right? That is the sample space. Now, find the probability that all 3 of her children are the same gender. So the probability of all 3 same gender. That is the probability I am calculating, that all 3 have the same gender. Well, I can use the classical approach here because I have all of the outcomes listed. Each one is equally likely to occur, right? Because any given outcome is equally likely when I have all possible outcomes. Boy, boy, boy is just as likely as girl, 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 is just as likely as girl, boy, boy, right? Each outcome is equally likely. So, I'll put 8 in the bottom because there's 8 total. Now, how many of them have all 3 the same gender? Well, all boys or all girls would count. So I could say 2 out of 8, which that reduces to 1 over 4, or 0.25, or 25%, right? Those are 3 different ways to write that number as a fraction, a decimal, and a percent. Now, find the probability she has 2 daughters and 1 son. So probability 2 daughters, 1 son. I abbreviated 2D, 1S. So I'm looking for all the ones that have 2 daughters and 1 son. Grab our blue pen. 2 daughters, let's see, there was 1, 2, 3 possibilities that had 2 daughters in them, right? 1, 2, 3 of them had daughters in duplicate and sons in the single, right? So, 3 daughters, or 3 possibilities out of 8 total, which if I wanted to, I could convert that to a decimal. Let's see, what it would, as a decimal, I could do, let's see, 3 divided by 8 is 0.375, or if I so prefer, as a percentage, that would be 37.5%, right? We want to get used to all 3 different expressions, fractions, decimals, and percents. Now let's look at the third example. What is the probability that a dollar bill you own was previously owned by Robert Downey Jr.? Now, I have 3 options for my approach. Let's see. Let's look at the classical approach first. Can I write all possible outcomes for this procedure? No, there's way too many dollar bills in the country, right? There's no way I can track down every dollar bill and who owned them previously. There's no way I can write out all the possibilities. So I know it's not the classical approach. Did this question give me information about an experiment or a study or something that would allow me to use the frequency approach? No, it did not. So I have to use the subjective approach. So, for this, maybe I think it's really unlikely, right? There's a ton of dollar bills in the world, right? What's the odds that Robert Downey Jr., who probably spends most of his time in California, because he works as a movie star, right, had dollar bills from his wallet find their way into the Saranac Lake economy and then find their way into my wallet? Highly unlikely, right? Maybe I say it's 1 in 10 million. Or maybe I say 1 in a million. Or maybe I say 1 in a billion. Or maybe I say 1 in 7,324,972, right? It's subjective. For this sort of question, on a homework, you'd probably be given options. Which of the following is the most likely answer? And it might give you, 50%, 75%, 0.001%, or none of them. You want to pick 0.001%, right? It's unlikely that this is true. It's unlikely. That's a very low chance. So I use subjective probability. Now, our next example, in a recent study of United States drivers, it was found that 3,785 texted while driving in the past week. Shame. And 4,720 of them did not text while driving. Good on them. Based on this study, what is the probability that a randomly selected driver has texted in the past week? So I want to look for the probability of texted, right? I'm looking for who texted. Now I need to be careful. In my study, how many total people were there? I have to add the texters and the non-texters together to get the total. So let's take care of that first. We'll have to add the two different values together in the denominator to get the total, right? What about the numerator? Well, I'm interested in the probability of texted, so I'll take the number of adults who texted. 3,785. Now, you need to figure out the bottom before you can divide, right? That's algebra, right? You got to figure out the bottom before you can divide. 3785 plus 4720 gives me 8505 in the bottom, 8505 in the bottom, and I have 3785 in the top. That looks like a fraction that I could maybe reduce, but I'm going to make it a decimal. Let's just divide it right away. 3785 divided by 8505 gives me, let's see, 0. And I'll round to 3 significant digits, right? 3 decimal places. 0.445 or 44.5%. Here, decimals and percentages are a lot more useful to me than the fraction is. 3/8, I know how the number 3/8 works. 1/4, I know how 1/4 works. 1 in 10 million, I get the gist. 3,785 out of 8,505. How does that? Where does that fraction fall? Is it bigger than 50%? Is it less than 50%? Is it, this fraction isn't very helpful, right? So it might be more intuitive, or I might get a better grasp of what's going on by looking at the decimal or the percentage. So keep that in mind. Always be comfortable converting between the different values. Now, we have a fifth example. In our fifth example, it says in the United States, Thanksgiving always occurs on the 4th Thursday of the month. So the question gives me some background information. It says Thanksgiving always occurs on the 4th Thursday of the month. What is the probability that in the year 3217, Thanksgiving will be on a Wednesday? Given what the question said, it said it always occurs. So what's the probability of Thanksgiving on Wednesday? What's the probability? If it's always on the fourth Thursday, is it ever going to be on Wednesday? No. The probability is 0 or 0%, depending whether I want the decimal or the percentage. Thanksgiving will never be on a Wednesday because it's always on the fourth Thursday. Now, what is the probability that in the year 3115, Thanksgiving will be on a Thursday? Well, if it's always on a Thursday, so the probability of, I'm going to write TG for Thanksgiving on R for Thursday. T is Tuesday, I use R for Thursday. Well, it's always on a Thursday. This will be 1 or 100%. Decimal versus fraction. Or sorry, decimal versus percent. Decimal is 1, percentage is 100%. Make sure you're comfortable with both notations. So notice here, I had to use this given sentence, right? I had to use that sentence to think about it. And this gives us a nice segue into what are called certain events and impossible events. A certain event is an event A with P of A equal to 1, which, remember, 1 is the same as 100%. It always happens. It can never not happen. For example, when I roll my die, what's the probability I get a number less than 10? I'm always going to get a number less than 10, right? Numbers are 1 through 6. They're all less than 10. It's certain I will roll less than 10. If I'm playing Monopoly and I'm rolling my 1 die, that might be a bad example. You roll doubles. You roll 2 dice in Monopoly. Maybe I'm playing a board game where I roll 1 die, and I got to roll a 7 to win. Can I do it? Can I roll a 7 on 1 die? No, right? I know it's certain I cannot win, right? Because it's impossible to roll a 7. So an impossible event is an event, let's say B, with the probability of B equal to 0, which as a percentage, remember 0 is the same as 0%. So an impossible event can never happen. What's the probability when I roll this die, I roll a chipmunk? That wasn't it. That was the number 2. That was the number 6. I'm not rolling any chipmunks, because there's no chipmunks in the die, right? It's impossible for me to roll a chipmunk on a die that's numbered 1 through 6. Now, if I painted a chipmunk on this face, then I could roll a chipmunk, right? But it's impossible to roll a chipmunk. Now, a complement for an event A. The complement of A, which is denoted A bar. It's denoted A bar. Excuse me. It's denoted A bar with a little bar over top of it. The complement of A, denoted A bar, is the collection of all events that are not A. It's all the other possibilities. So maybe my event A is rolling a 4. The complement of A would be a 1, a 2, a 3, a 5, or a 6. It would be the opposite. That's what the complement is. Some people like to remember this by thinking of complementary colors. They're opposite sides of the color wheel. Now, based on the previous skydiving study, what is the probability of surviving a skydiving attempt? Well, let's look back at the skydiving example. Here it is. So based on the previous skydiving study, what is the probability of surviving a skydiving attempt? Well, it said there were 3 million skydiving attempts. So I want the probability of surviving. Now, there's still 3 million total procedures being run, right? The experiment still had 3 million. However, if 21 of those skydivings resulted in a loss of life, how many didn't? How many resulted in survival? Well, it'd be 3 million take away 21, right? All the other skydiving attempts did not result in a loss of life. It'd be the opposite, right? I can subtract to get the value. Now, in the top I gotta subtract. I'm gonna get 2,999,979 when I subtract, right? 3 million minus 21 gives me 2,999,979 over, still got 3 million in the base, right? I want to divide these, divide by 3 million, gives me 0.99993, or if I make it a percent, it'd be 99.9993%, right? Which should make sense. If it was unlikely to perish, it should be likely to survive, right? That just makes sense, right? They're opposites. So there's an example of using the complement. And then we have a brief summary of some probability basics. The first, I've already said it, but I want to remind ourselves, is that probabilities can never be bigger than 1 or less than 0. They're always between 0 and 1. Or, if you prefer percentages, they're always between 0 and 100%. Now, another basic of probability is that the probability of the complement of A plus the probability of A should always equal 1, or if you prefer, 100%. If you take all the events that are A and all the events that are not A and add them together, that should cover everything, right? It's either A or it isn't A, right? It either is or it isn't. So that should cover everything. These are some basics of probability. So keep these things in mind as we move forward. These will be useful, especially the first one here. You can know your answers are incorrect if you ever get a negative number or a number bigger than 1, or you ever get a percentage that's negative or a percentage bigger than 100. You will know you're incorrect. So keep these in mind. And that brings us back. Oops, I lost the first page. No, that's over here. That's right, I kept it separate. That brings us back to the first page because we have now finished our introduction to Chapter 4. Thank you for stopping in, and I will see you next time.